I have chosen the chapter Elasticity from grade 11. Elasticity, in one sense, is a common phenomena as we can see around us in our daily life. The rubber is stretched instantly regains its original shape when the applied force is removed, but within the elastic limit or within certain extent. I'm going to discuss this in reference to grade 11. The cause of this elastic force is the interatomic and intermolecular forces. The force between the atoms which keeps them bind to form a molecule is called interatomic force. And the force between the molecules which keeps them to give the substance a form or shape, specifically in solid intermolecular force, give the definite shape. The nature of this force is just like the spring in which if we compress the spring, the outward repulsion is developed, and if we want to extend the spring, the inward pull is developed, always opposing the applied force. So the intermolecular force has the same nature, similar nature. The nature of those forces is shown in the curve in right side. The red line, curved line represents the force, and blue line represents the potential energy. The point M shows the zero force. This occurs when the molecules are in an equilibrium separation, where the potential energy is minimum. Minimum energy state is most stable, so it is called equilibrium separation. Beyond the equilibrium separation, the force becomes attractive, or if you want to increase the distance between the molecules by applying force, the force becomes attractive. So the curve goes in negative axis, means the force is attractive. And if the distance between molecule is decreased by applying force, the force is repulsive. So it is on positive y-axis. What you have to remember is nature of intermolecular force can be compared with the nature of the spring. And we are discussing the intermolecular force because it is the cause of elasticity. The details shown in this slide may be more than required. So I want to go to the next slide. Uh, what is elasticity? Elasticity is the property of a body because of which they tend to regain their original shape, size, or say dimension after removing the deforming force. There are some substance which poses more elasticity than the other. Those substance which completely regain their original shape, size, and dimension after removing the deforming force instantly are called the perfectly elastic body. In practice, perfectly elastic body does not exist, but quartz fiber is good approximation of perfectly elastic body. Next, plasticity. Plasticity is the property of a body to retain the deformed shape, size, or dimension even after the deforming force is removed. Now, you have to be careful with the words which I have highlighted to know the difference. Elasticity is the property of a body to regain original shape and size, but plasticity is the property of a body to retain, means keep the deformed shape. Perfectly plastic body. If a body retains its original shape even after removing the applied force or deforming force completely, it is called perfectly plastic body. The good approximation of perfectly plastic body is putty, which is animal fat, if you know it. Now, stress. Stress is defined as the ratio of restoring force to the area. Since the restoring magnitude of restoring force is equal to deforming force, we can also define it as the ratio of deforming force to area. The unit, SI unit of stress is Newton per square meter, just like the pressure. Stress is developed because of pressure. Now, types of stress: normal stress and tangential or shearing stress. If the applied force is perpendicular to the surface, the ratio of force to area is called the normal stress. There are two types of normal stress, as you can see in the figure attached on the right side. If the applied force increases the length of a body, the corresponding stress is called tensile stress. If the applied force decreases the length of the body, or say dimension of a body, the corresponding stress is called compressive stress. I want to show you the animation to express the tensile stress and compressive stress. The first animation shows the tensile stress, which is increasing the length of the body. And the second animation shows the compressive stress, which decreases the length of the body. Now, tangential stress or shearing stress. If the applied force is parallel to the surface, the corresponding stress is called shear stress or tangential stress. Shearing stress deforms the shape of the body. Now, strain. Strain is the fractional change in dimension of a body because of deforming force. So it is expressed mathematically as the ratio of change in dimension to the original dimension, or change in configuration to the original configuration. Since it is the ratio of like quantities, strain is unitless and dimensionless. According to the applied force or stress, strains are of different types. First is longitudinal or tensile strain, bulk strain or volume strain, and next shearing strain. The longitudinal or tensile strain is defined as the ratio of changing length to the original length. Bulk strain is defined as the ratio of change in volume per unit original volume. The figure also clarifies the definition. You can check on the right side of this slide. Shearing strain. Shearing strain is defined as the angle through which the body is deflected by the application of deforming force. It can also be defined as the ratio of the lateral displacement of the body to the length of the side perpendicular to the force applied. So theta is equal to x by L, which can be easily proved by using simple trigonometry of the figure 3. Elastic limit. Elastic limit is the maximum value of stress that can be applied or that a body can bear without going permanent deformation. Now, Hooke's law. Hooke's law stressed that the elongation produced on a body is directly proportional to the force applied within the elastic limit. So we write F is directly proportional to E. Mathematically manipulating in few steps, we can express Hooke's law as stress is directly proportional to strain. From this expression, F is directly proportional to E, we divide both sides by area. Then further manipulation on the right side, dividing and multiplying by length, we get stress on the left side, force per unit area, and strain E by L inside the bracket. And the term and the ratio length to area is constant for a given material. So this is involved in the proportionality sign. And this form of statement of Hooke's law gives a definition of an important quantity, the modulus of elasticity, as the ratio of stress to strain. Modulus of elasticity has same unit and dimension as the stress because strain is unitless and dimensionless. Depending on the type of stress and strain, modulus of elasticity are of different types, which we will discuss on next class.